In the year 2023, a colossal meteorite rivaling the size of Pluto hurtles towards our solar system. As it breaches Saturn's orbit, a squadron of probes converges on it, only to return empty-handed, having detected no minerals. Meanwhile, at the Space Security Center in Alaska, military personnel set up a laser. Suddenly, the solar system witnesses a brilliant flare, leaving no trace of the dwarf-sized celestial body. Unless hydrogen miners on Jupiter document another obliteration on social media, this is the world we envision when humanity attains the coveted status of a Type 2 civilization on the Kardashev scale. At that juncture, we would possess nearly boundless reserves of energy, the capability for interstellar journeys, and the power to obliterate threats instantly. However, the question looms: will humanity truly be secure, and what potential perils could jeopardize a Type 2 civilization to ascend to the second echelon on the Kardashev scale? Humanity must glean energy not solely from terrestrial sources, but directly from the sun. We do not refer to conventional solar panels, but rather an extensive megastructure encompassing the star. A Dyson sphere. This ingenious design, conceived by Princeton University's Professor Freeman Dyson in 1960, entails a colossal shell enfolding the star and its proximate planets. This sphere would harness all of the star's energy, converting it into electricity while radiating excess heat as infrared radiation. The expanse of this colossal construct stretches to 1 astronomical unit, akin to the Earth-Sun distance, with a material thickness of approximately 3 meters. Constructing a Dyson sphere would present a formidable challenge, primarily due to the colossal resource demand. Estimates hover between 1.5 to 10 to the power of 24 tons of material, exceeding even the mass of Jupiter, the largest planet in our solar system. Thus, humanity would necessitate the processing of all accessible asteroids and even the disassembly of several rocky planets to harvest the requisite materials. Moreover, the structure must achieve perfect sphericity to evade the sun's gravitational forces, crumpling it into a mere foil ball. The materials must also exhibit unparalleled strength, as even the most advanced carbine, considered superior to graphene, proves unsuitable for this purpose. And yet, even if the monumental endeavor succeeds, stability remains a pressing concern. The star within the Dyson sphere must remain impeccably centered. A slight deviation, say from an external meteorite collision, could lead to the sphere's drift towards the sun, culminating in collapse. This challenges the feasibility of constructing such a gargantuan edifice. However, Freeman Dyson's concept deserves a second look, rather than a solid structure. Dyson's sphere comprises an array of diminutive satellites enveloping the star, capturing its radiation and beaming energy to Earth or other receptors through wireless transmission. This Dyson swarm, as it is termed, sounds decidedly more pragmatic. Naturally, implementing this would necessitate advancements in wireless energy transmission technology. Still, even this approach necessitates a formidable resource pool. To erect a single ring or a satellite system, humanity must access significantly more resources than the Earth presently affords. This leaves us with little recourse but to seek materials beyond our home planet. Yet, disassembling Venus or Mars for materials may inadvertently alter our planet's orbit, posing a perilous consequence. Moreover, a fully realized Dyson sphere would obstruct sunlight from reaching planets beyond Earth's orbit, rendering the colonization of Mars and exploration of Pluto a distant dream. Additionally, initial solar flares could potentially disable any megastructure encircling the Sun. Yet, the crux of the issue lies in harnessing the colossal energy output of our star. If we manage to intercept even a modest 10% of it with a Dyson sphere swarm, we'd command an inconceivable power resource, surpassing current global consumption by a staggering margin. The most efficient approach would be converting sunlight into antimatter, a prospect fraught with its own challenges. Storage methodologies for antimatter remain largely theoretical, with potential risks of catastrophic explosions looming. In conclusion, the pursuit of a Type 2 civilization, while promising boundless potential, is fraught with complexity and dangers at every turn. From the initial design and resource requisites to energy storage and utilization, the challenges are manifold. Even if we overcome these hurdles, the question of how to best employ such a staggering surplus of energy remains. The path to Type 2 civilization may well redefine our understanding of physics and energy dynamics, The future, it seems, holds both tremendous promise and perils aplenty.